All right, so we are going into our second lesson in the series of evolution and the Bible, quite dealing with the question of do science and the Bible work together? And so this recording is for those who missed the second lesson so that you guys can catch up if you want to. You're welcome to watch this video. So I'm just going to basically go through the lesson, teaching it just as I taught it on Wednesday night, but I'm going to do it just through the slides, so with my voice over the slides. So bear with me if this is a little different than a normal evening, but do my best to make it as natural as possible. So this next lesson, last week we did kind of an overarching view of what the theory of evolution is, how what its principles are, looking at playing that game with the cups where we talked about the issue of overpopulation and the need for a fight for resources between creatures, and then they have different adaptations that make them more adept at getting that food, and then some of them that don't, that they die off. And then Darwin went on to say that those species kept changing and changing until eventually you had something change into a completely different species. For example, the dog changing into something like a dragon. Now, he didn't exactly say dogs would change into dragons, but that's just an extreme example for the sake of you understanding what that his last point was. And we also talked about how we can know that the Bible, when it talks in Genesis, talks about a literal 7-day creation. And that one of the big ways that we talked about that was through using the word yom, which is the Hebrew word used for day in the Bible. And it is the one that's used in the Genesis account there. And through the context how that's used, we can know that and every other case where it's used with words morning and evening, or a time, or used in context, that we would see it used in Genesis 1, that it is always meaning a literal 24-hour day rather than a figurative one meaning thousands or millions of years. So we talked about some other stuff, but that's just gives you a general recap of our last lesson. In this lesson, we are going to talk about probably improbable, and so we're going to talk a whole lot about the odds of evolution. I'm a big Star Wars fan, so I had to throw in this GIF here. But really going to focus in today on the odds of evolution. We're going to start that conversation out by going over the second law of thermodynamics. And that is a law of physics, rather complicated sounding, but we're going to explain it for you, hopefully in simple terms. And the way we did this last night was I had in a bag, a little clear Ziploc bag, I had taken a flashlight apart, and I had the batteries out, and I had the battery casing out, and the lid off, and the housing for the flashlight all in this bag. And I gave them all a challenge to put the flashlight together simply by shaking the bag. And so we passed the bag around the room, and they were shook and shook on it to try and put this flashlight together. They couldn't actually manipulate the pieces in the bag, but just had to shake it and try and get it back together. And so we passed it around the room, and it did not go very well. In fact, the bag eventually busted, and pieces were going everywhere. Uh, Needless to say, didn't work out for us to get this flashlight together. And that is because of the second law of thermodynamics. Now, I'm going to give you the technical definition, then we're going to explain what that means a little bit for you here. The technical definition is that as energy is transferred or transformed, more and more of it is wasted. The second law also states that there is a natural tendency of an isolated system to degenerate into more disordered state, blah, 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 blah. That's very complicated. That's a really complicated way of saying that things get worse over time unless you put energy into fixing it. So what I mean by that, when you clean your room is going to be it'll stay clean for a little bit, but what happens to it over time? It starts to get messy. After a little bit of time, you got dust that settles. You don't pull something out, don't put it away, and it clutters up. And before you know it, your room is a mess. And so uh, over time, things always get worse unless you put energy into fixing it. So unless you take the time and energy to fix your room and clean it up and put the stuff away and dust and vacuum and just make sure that your room gets cleaner. That's how the only way things get better is if energy is inserted into a system. That's what this law of physics, the second law of thermodynamics, says. So we saw this exhibited in our illustration where we had that flashlight in a bag. What happens is another part of this law is that chaos never creates order. And so we have these pieces of flashlight in a bag in a state of chaos. And so shaking them just institutes more chaos into the system. And so you have this chaos and chaos and chaos that goes on. And before you know it, instead of things getting better and more orderly with the flashlight coming together, what ends up happening? In fact, our bag started to rip, pieces flying everywhere. Things didn't work out very well for us. So you have this issue here where things always get worse, not better, unless I were to do something like actually manually put that flashlight together and put that energy into making it orderly. And so, give you another example, you're never going to have a tornado hit a trailer park, and it's never going to turn into a Boeing jet. You're never going to have that happen. Not no matter how many times you send a tornado into a trailer park, it's just all those pieces aren't going to come together in such a way that you have a Boeing jet that's created. And so, but the thing about it is that evolution states that everything did get better over time after a chaotic event. And so, to give you a little recap of what the theory of evolution states, apart from just the biological stuff that we talked about last week, essentially, evolution says that billions and billions of years ago, there was this ball of matter. Just stuff that was floating around the universe. It was there. It's always been there. It was always there, just this eternal ball of matter. And this ball of matter one day spontaneously combusted and it blew up. It just blew up, and out of that ball, it was called the cosmic egg. Out of that ball, the universe was formed. And so, as it expanded and expanded, rocks hit into each other, and atoms and everything were created, and planets were created from rock, uh, and the universe expands and expands even to this day as a result of this Big Bang that we've heard about before. Well, so what you have here, the problem with that is that evolution states that things got better after the Big Bang, not worse. You've got this stuff this explosion that blows everything up, and things are just randomly, chaotically hitting into each other, but they're getting better. They're getting more orderly. You have things that planets that are forming, and then on Earth, the planet, it formed this what they call this primordial soup, which is just this essentially this goop, this liquid that had all the necessary components for life that all just for millions of years just kind of bumped around against each other until the right ones hit each other, and life was formed into a single-celled organism that then slowly started to evolve and become more complicated through those principles of evolution we talked about last night. And here we are to everything we know today, billions of years later, all random accidental chance from chaos. But the problem with that is that we have a law of physics that we just talked about called the second law of thermodynamics that states that chaos never leads to order. And so what that means is that either that law did not mean a thing, it wasn't ever in play, it never, that was not a law of physics for billions of years, for most of time, until the past few thousand years, or or that the Big Bang broke the laws of physics. Um, and then our other option is that the Big Bang just didn't happen. And so we really have an issue here when we have this law of physics uh, that the Big Bang somehow violated. But let's say, let's just say that that all did happen. Somehow that all happened. So our question is going to be, what is necessary for life? Because, I can bang a flashlight around and pieces together, and maybe, just maybe, if I shook it just the right way at just the right speed for just long enough, I would get a flashlight put back together, and somehow the batteries would seat themselves in the correct order, and the cap would somehow screw itself on. All that. In the end, I don't have something that's alive, I have a machine, I have a flashlight. So life itself is much more complicated than just rocks forming into planets. If that was all that happened, it might be a little more believable. But what they say is that then life itself was created. So the question is, what is necessary for life? And so before I go into this, I want to remind you guys of nursery rhyme of Goldilocks. So you know the nursery rhyme of Goldilocks. She goes into the three bears' house, and she's she goes to the bed, and one's too hard and one's too soft, but the other one is just right. And she tries the porridge, and one's too hot, one's too cold, the other one is just right. And so everywhere that she goes, she's not everything's either too hot, too cold, or just right. And so when it comes to making life, the conditions necessary, you're going to find it's very similar to Goldilocks, called the Goldilocks principle here. Uh, it's either going to, you can't have things be too hot, you can't have things be too cold, you need them to be just right. And that just right window is a very small one, and so we have to make sure that happens. So let's go into what some of the things necessary for life are. So first of all, we need a planet that can host life. So if we don't have life, or a planet that can host life, then obviously life can never form in the first place. So what goes into having a planet that can then host life? Well, the first thing is the thickness of the Earth's crust. So you've got this hot center called the Earth's core, and it's filled with magma and just molten hot liquid, and you have this layer of rock that's between us and the crust. Okay. Well, let me explain this with an illustration for you. Let's say that that I placed a spoon on top of the eye of a stove and turned the eye of the stove on until the spoon was red hot, like it was glowing hot. What would happen if I grabbed the spoon? Well, I'd burn the snot out of my hand. It would hurt. So instead of just grabbing it with my bare hand, let's say that I took a tissue like a Kleenex and I put it over the spoon and then I grabbed it with my hand. Uh, what would then happen? Well, I'd still burn the snot out of my hand, but I might do it just a split second slower than I did last time. Um, but then let's say that we go on and I put a towel, like a thick towel over it, and I grabbed it. Well, it might eventually burn my hand if it was hot enough and I held it long enough or the towel was thin enough. But I could actually grab it up off the stove without pain, or an oven mitt would do the same kind of thing. That's the principle of oven mitts, puts a distance between you and it. That's what our Earth's crust does. It is such a thickness that it keeps our Earth warm. It stays a sustainable temperature for life to exist on it. That it's not too hot. If it was any thinner, the lava and magma would be much closer up to the Earth, and we'd have more volcanic activity. We'd have all kinds of issues, but it would make the Earth too hot. If it was much thicker, then the core couldn't warm the Earth in such a way that the planet was warm enough for life to exist. So we have this crust. The planetary crust is the exact thickness that the temperature is what we need it to be for life to exist. Okay, so that's our first condition. We need a planet with the right thickness crust around the core. Okay. Next, we need a magnetic field. So we need a magnetic field that is just the right size so that the sun's rays, the radiation coming out of the sun that is attacking the Earth, uh, that it doesn't burn us all up. Your microwave uses radiation to heat things up, so it can heat things up. It can literally burn something, and so the sun has all of this very dangerous radiation that's coming off of it, and our magnetic fields deflect that around us some. We still get some that comes through, and that's okay. We need that to warm Earth. That's how you get a suntan, as you go outside and some of that radiation actually hits you. Some of the sun's rays make it through the atmosphere and this magnetic field, but we need most of it to go around the Earth, and that's because with we don't want to fry. We don't want to be in a giant microwave oven that burns us to a crisp. And so we have to have a correct magnetic field. Not all planets have the size one that Earth has, but we do. And so we are very fortunate in that we have that magnetic field. So what's next? We've got the crust, we have a magnetic field, our atmosphere. So the atmosphere is incredibly important. The atmosphere is such that you have oxygen rich. Atmosphere is what holds all the gases inside the planet. And so we have an oxygen rich atmosphere, which, as you know, oxygen is necessary for life. If you've ever been up to a really high altitude where there's a lot less oxygen than down here, you'll find that you very quickly miss it. You're very tired and exhausted and sometimes even sick without the right amount of oxygen. So not just do we have some oxygen, but we have an oxygen rich atmosphere, one that is filled with breathable gases that we need for life. Not all planets have that. Some have very poisonous atmospheres. For example, Uranus is filled with methane, which I think, as a side note, is kind of funny because that means that Uranus smells like farts. Uh, and so we've got this. Uh, Not all planets are such that the gases on them are sustainable. They are such that our life cannot exist on many of them, but ours does. Ours has oxygen. So, Earth's crust, magnetic field, atmosphere, and water. We need water. Obviously, water is necessary for life. Why do you think it is that NASA is always looking on other planets and moons for signs of water? They're looking, at ice caps and that there are signs of water. Well, one, it's so that, if we ever do space travel or Earth is overcolonized, that we can go live on those other planets and exist there. But the other reason is because they're looking for aliens. They're looking for life elsewhere. Surely in this giant universe, aliens exist. Is what they're thinking, and so they want to find evidence that aliens could live, and the necessary thing for that is going to be water. And so our planet, luckily, is about 80% water, so we've got plenty of it to go around, and that makes it a very good place for life. It's not all water, so we actually can live on it on land as humans, but we do have a lot of it to go around. The next thing that we need in a planet is a moon, but not any moon. We need the right size moon. So some planets have really big moons, some have really small moons that are not much more than rocks that float around them. The Earth has our moon, and that is the perfect size. And what it does is it regulates the tides, but it also acts as a balance for the Earth. So as it swings around the Earth, it keeps the Earth stable in its rotation and consistent in its rotation in such a way that it actually regulates the seasons. So you can thank the moon for summer, fall, winter, spring. All of those seasons you can thank the moon for because it is regulating the rotation of the Earth in such a way that it's consistent. And so we don't have, some years summer isn't 10 months long, whereas the rest are all fit into a few. Like we can predict what the seasons are. That is because of the moon. And what seasons do, whether you like all of them or not, are they maintain a mild climate on Earth. So that again, not too hot, not too cold, just right. We have just the right temperature on Earth for us life to live. All right, so the next thing is the size of the sun. So we've got the moon, but the sun is also very important. The sun is actually not the biggest star in our solar system or in the universe at all. In fact, it's actually a relatively small star, all things considered, but ours is the perfect size for what we need. And the reason for that is one, the heat that comes off of it. But if you think about the sun, imagine with me that there was a ring around the sun. If there's not, but just imagine for me that there's this ring, and in that ring is the safe space that life could exist. Well, there is such a thing. That's not a literal ring, but it's called the habitable zone, and it is this small space around the sun that life can exist. The conditions in that space are good for life. And guess which planet happens to be the only one in that zone? Earth. And the reason that this zone exists is because that is the distance from the sun that the sun provides just enough warmth for us, and the gravitational pull is not too strong for us as we rotate around the sun. We are in this perfect spot that life is it's mild enough for life to exist. Now, if the sun were any smaller, what that would do is that would shrink the habitable zone in much closer for that temperature side of things. But the problem is that the closer you get into a big body like the sun, the stronger the gravitational pull is going to be. And so, what would happen is actually, if we were to get in closer to the sun, we would have the Earth would be pulled into a gravitational rotation around the sun that made it so the Earth only ever one side faced the sun. So one half of the Earth would always be daylight, and it would be up close to the sun, and it would scorch the Earth. And the other half would always be nighttime, and it would freeze the Earth. And you would never have it in such a way that it rotated like our Earth does around the sun. And it's because that gravitational pull would mess with things. And so we can't have a smaller sun because then that would force us to be up close. But it's still, even though the temperature would be right in that habitable zone, it messes with the rotation of the Earth. So again, we get too hot or too cold or both, actually, with the size of the sun. Okay? So the odds of all these things happening together The crust, the moon, everything, all that together are a thousandth of a trillion. So that's pretty bad odds. In fact, if you were to tell me that I had a thousandth of a trillion chance of making it to my destination when I hopped in the car without dying, I would probably stay home because those are pretty bad odds. It is incredibly unlikely that all of that just happened randomly through a big explosion. That all those conditions for a planet to be necessary for life to exist, all of them happening randomly together, it's a thousandth of a trillion odds. But let's just assume that all that somehow did happen. What else would be necessary for life to exist? Well, we talked about our solar system and our planet, but really, we also need to have the correct spot in the universe. So, where we are in the galaxy actually matters. So, we're in the Milky Way galaxy, and in the Milky Way galaxy, we are right there, that blue spot. Now, that blue spot is not representative of Earth or even our solar system, it is not to scale. In fact, our solar system is so small that it would not even you couldn't even picture it as a pixel on this screen, and so it has to be. It is in the scale of the of the galaxy. It is just the smallest of dots, not even a dot on that system, and then the Earth is within that solar system. But we are right there. We're not in the center. We're not on the edge. We are about right in the middle of the Milky Way galaxy there. Uh, and so the thing about it is that we could not be where we're at in the Milky Way galaxy matters. We can't be closer to the center because we would burn up. In the center of that galaxy right there, that little yellow section there, is a lot of radiation. It is just all this radiation that's there. And so we couldn't, if we were to go up again, remember what happens with our magnetic field and that we can't have too much radiation. In the same way, we would cook if we were in the center. The earth would literally be on fire and scorched. It would be terrible. So it's not good for us to live in the center. But we also can't live too far to the edge because outside on the edge of the Milky Way galaxy, there are these stars that blow up. And the stars release these heavy metals that are very poisonous. So when I say heavy metals, I mean things like lead, cadmium, things that are very poisonous and high concentrations to life, and they would coat the earth and we would be poisoned and die. So we couldn't have life out there on the edge either. But it's not just that. We can't be too close, but we can't be too far on the edge. But we also can't be in one of those spiral arms. If we're in one of those spiral arms, those are not very nice places either. They actually are very deadly, and there's a lot of activity that happens there that would kill us very fast. Think about being in the center of a tornado, and that's kind of what it would be like for us. It'd be very dangerous for us out there. So we have to somehow be not too close in, not too far out, and not in an arm, but somewhere in the middle outside of a band. And that is, excuse me, that is where we would have to be. So, all of that to say, that is incredibly unlikely. But having the right position in the galaxy and having the right planet, all of that, all those terrible odds are actually the easy part. So let's just say the easy part happened. Let's say that somehow we got all those conditions randomly from the Big Bang, it broke the laws of physics, everything happened, and we get to that point where now the conditions are right. We have this primordial soup, we can make life. So what's necessary for life? Well, the first thing that we need for life are proteins. It's not just what you eat in meat. Meat has that protein in it. Yes, that's part of it. But when I say proteins, I'm actually talking about what we scientists consider to be the building blocks of life. You need proteins to make cells. And they all go together kind of like Lego bricks or building blocks to make a cell, and a cell is necessary for life. In fact, it says that life started with a single cell, a simple single-celled organism in that soup. And so, in order to make proteins, let's say that we're going to go into our kitchen, we're going to make up some proteins. Well, we're going to need amino acids. That's our ingredients. And so amino acids, there's about 300 plus of them, and each of those X's represents one. But the thing about amino acids is that out of those 300 plus, only 20 of them are used for life. So those red X's represent the amino acids that are actually used for life. And so you can't just, any amino acid won't do. You have to have one of those 20 to do life. But it gets harder. Not only do those 20 are they the only ones that work, but there's two types of every amino acid. So you have a left-handed amino acid and a right-handed amino acid. They're mirror images of each other. They're the exact same kind, but out of those 20, the only ones that work are the left-handed ones. So you have to have a left-handed amino acid of those 20 to bind together to create a protein. But even then, you can't just have all of those in a pool together and they magically form a protein. They have to be in the correct order. So the order of them is very crucial. If they are in an incorrect order, you get you get bad things, or you just simply don't get a protein. But when you get them all together in the correct order, you can then fold up those amino acids into a protein. So that is what happens when we have all those. But all those conditions have to be met for a single protein to even be made. Now, the thing is that proteins, they range in size. They range anywhere from 15 amino acids to about 30,000 amino acids. So let's say that we are going to cook up in our kitchen a simple protein that is only containing 100 amino acids. So we got a pretty simple one here. And so with that amino acid, with those amino acids all coming together to create this protein, 100 of them together, what are the odds of that happening randomly, just by accidental chance, again in this primordial soup all together? The odds of that happening randomly are going to be 1, 2, that's a lot of zeros there, but what that number is 1 to 10 to the 130th power. So that's 130 zeros right there that you see. And that is your odds of all that happening randomly, all the correct amino acids coming together to create a simple 100 count protein that you would need just to make a cell. Now, that's pretty bad odds, but that's even worse than our earlier odds. But let me put this in perspective for you. So in our lesson, we talked about flipping coins. So I had 3 people come up and flip a coin. And when they came up and then we flipped quarters, I gave them basically 2 shots. I told them to try and get heads as many times as possible in a row. If they got tails, they were out. But I was going to give them 2 chances so they could flip it. If they flipped it 5 times in a row and then got tails, I'd give them another shot to try and get as many heads in a row as they could. If they just right off the bat got 2 tails in a row, they were out. So we had 3 of them do it. One got out immediately. The other one got 4 in a row and then flubbed up the second time. And then the third one flubbed up the first time, but then they got 5 in a row. So our record was 5 heads in a row. All of us flipping these coins here. So 5 in a row. But for those odds that I just showed you to happen, if we were to translate that to flipping a coin, it would be like me telling you that you had to get heads 100 times in a row. And you couldn't ever have tails in there. It had to be 100 heads in a row. It's possible. It's highly unlikely. So to make those odds possible, this is what you would have to do. You would have to flip that quarter 300 million times a second for 1 quadrillion years. 300 million times a second for a quadrillion years. So remember, evolution says everything happened in a few billion. But for a single protein to accidentally be made, it'd be like you flipping a quarter for 100 times to get 100 times in a row, and your chance at making that happen would come at 300 million times a second for a quadrillion years. Those are your odds of getting a quarter 100 times in a row. But it gets worse. The news just gets worse for us. Evolution says all this happened by chance. We have a simple celled organism that happens, and slowly it evolved into creating something like a human. Well, if you want to take a guess at how many proteins are necessary to create a single human cell is composed of 42 million proteins. Now remember, some of those proteins can be made up of 30,000 amino acids, and again, out of those 300 amino acids, only 20 work for life, and the left-handed version of those work, and then they have to be in the right order. So for a single simple celled organism, granted it's a little they could say it was a little simpler than a human cell, but let's say for a simple single-celled organism to form in that primordial soup just completely randomly, you would have to have around 42 million proteins that existed. Remember how hard it was for us to just have 100 amino acid protein, a simple protein, form a single time. Now, humans, it would eventually have to evolve to a point where it was a full human, which contained a lot of cells, and those cells actually even regenerate themselves over time. They have 30 trillion cells in them, and each of those cells has about 42 million proteins. So knowing all of that, how can this happen by random accidental chance? The odds are so against evolution creating this just randomly. And so it leaves us with a question. Is there a better explanation? Well, yes, there is. And you probably know what I'm going to say. But before we go into it, I just want to talk about Legos, because Legos are really cool. I don't know if you're a fan of Legos, but I am. I loved Legos. And let's say that I were to give you this Lego set that's there on the left, and then the instructions with that Lego set. And so the Lego set, we unpackaged it, we put it on a table. And I said, all right, I want you to put it together, and the way I want you to do it is I want you to unpackage it, put the instructions out on the table so we know how to do it, and leave it for a day, and we'll come back, and it'll be done in the morning. That's ridiculous. That wouldn't happen. You would never have that happen. The way it would happen is if you think about it, you would need to put it together yourself. You need an actual creator to take those instructions, read them, translate how you get them all together, and then put the pieces together in the way the instructions said, and then you get a little race car there. So you have to have a creator, and that is actually a principle that Einstein said, and it's called Einstein's Gulf. And his idea is that there's this canyon, this gap between conceptual ideas, theoretical ideas, and actual concrete things. So what I mean by that is that Lego set could never become these Lego instructions can never just build a car on their own. They need a person to bridge that gap, that canyon, to take them from something conceptual to an actual race car. You need a creator. And so that's what Einstein said, and that is a scientific principle. And I think what's cool is that the Bible, in the first verse of the first chapter of the first book, the first words give us that answer, give us that creator of how we bridge that gulf. In the beginning, God created the heavens and the earth. And so I think that is just really cool that we have our answer right off the bat. God didn't even beat around the bush. He just gave us our answer. This is how life began. It wasn't random. It wasn't accidental. I formed the earth. I, being God, he put everything together. He was able to form the amino acids into proteins and to more complex structures that created life, and he created all of that. We see in Isaiah 45:12, he says, I made the earth and created man on it. It was my hands that stretched out the heavens, and I commanded all their host. And so I want to finish off here by showing you a video. And so this is kind of how we concluded. And I just want to finish off with this video here, and just take a minute to watch it. It's about 7 minutes long, and then we'll be done with the lesson here. And so we're going to start that, and I'm going to stay quiet.
You are back there. That's awesome. Yeah. But we are here tonight to worship. This is an amazing thought. A God who is indescribable. You say, well, how do you know that? All you have to do is walk outside on a dark night and look up into the sky, and you will know when you look up that this God we're worshiping tonight is beyond our wildest dream. The scripture says, by the word of the Lord, the heavens were made, the starry host by the breath of his mouth. We live in a little subdivision in the universe called the Milky Way galaxy. In case you didn't know, that's where you live. Some of you are thinking you live in Shady Grove. No, you're living in the Milky Way galaxy. That's your subdivision in the universe, a very big universe that we have to use something called a light year to get around in. You say, well, what's a light year? Well, that's how fast light travels in 1 year. And we know it's flying 186,000 miles a second. So if light goes 186,000 miles a second for a whole year, it goes 5.88 trillion miles in a year. And that's the measurement, or one of the main measurements we use to get around in the universe that God has created. That's how big it is. The foot, not going to help you in God's universe. The yard, of no value to you whatsoever in God's universe. The mile, insignificant. The kilometer, Matt, not going to help you getting around in God's universe. We have to use a ruler that is 5.88 trillion miles long to measure things in God's universe. And our home subdivision, the Milky Way galaxy, just came into being. It consists of billions of stars. Just our subdivision, the Milky Way galaxy. Not hundreds, not millions, not hundreds of millions, billions of stars in our home subdivision, the Milky Way galaxy. And scientists say that there are hundreds of billions of other subdivisions and galaxies in the known universe. This shot is where we live. It's a little snapshot of the Milky Way galaxy. If you zoom into this star-forming region, you see something pretty amazing. This particular shot is a close-up of a star-forming region in our subdivision taken by a friend of ours named Dr. David Block, who's an astronomer down at Wits University in Johannesburg, South Africa. And we were down there a few months ago, and he was telling us that if we were to count the billions of stars in the Milky Way galaxy, 1 star per second. So if we just started with any one of these, I don't know which one you want to pick. Let's just start with this one right here. And because I can reach it. And we start 1, 2, 3, 4, 5. That looks like 1, but I'm close enough to see it's 2 that are close together. 7, 8, 9, 10, 11. Let's go back over here. 12. You're like, oh, please don't count them all. If we counted all the stars in our subdivision, 1 per second, it would take 2,500 years just to count the stars in the Milky Way galaxy. And God says about himself, you want to know how the universe is telling us that God is big? Through the prophet Isaiah, he says, to whom will you compare me? And who is my equal, says the Holy One. Lift your eyes to the heavens. Who created all of these? And then he answers for himself. The one who leads forth the starry host one by one and calls them each by name. Because of his mighty strength and great power, not one of them is missing. If you want to get a glimpse of it, here's a composite shot of our subdivision. The Milky Way galaxy is taken by combining hundreds of thousands of photographs. Obviously, we haven't managed to get outside of the Milky Way galaxy to take a picture of it, but NASA folks are pretty sure that's what it looks like. It has a barred nucleus. It's a barred spiral galaxy. And you're like, wow, that's pretty cool. Yeah, it's 100,000 light years across. So if you want to go visit your neighbors on the other side of the subdivision, you just have to go 186,000 miles a second for 100,000 years, and boom, you're at their house. In our little neighborhood home called the Milky Way galaxy. You say, well, where are we? I'm looking for us on there. You know, we got to be right in the center, obviously. I'm sure we're right there in that middle. No, believe it or not, we're not even in the center of our own subdivision, okay? So affirming again tonight, it's not about you and it's not about me. We don't even live in the center of our own subdivision, and you don't want to live in the center of the subdivision because it's scary in the center of the subdivision. You say, well, where do we live? Well, we live way out between a couple of the spiral arms. You don't want to live in there either because that's dangerous territory inside the bands. We live in that little clear zone between a couple of the bands, about 2/3 of the way out. We're living somewhere about there. And you're like, well, I don't see me. No, because we couldn't put a mark on the diagram that you could see that would be the right relative size to our solar system. You know, that's our little cul-de-sac in the subdivision, that we couldn't even put our solar system on here in relative size to the Milky Way galaxy for you to see. It's that small inside the Milky Way galaxy. Scientists say our solar system is the size of a quarter, and the Milky Way galaxy is the size of the North American continent. So our whole solar system is a quarter, in the size of an area as big as the North American continent. We're not that consequential in our own subdivision called the Milky Way galaxy. And somewhere in there is a star, one of these billions of stars. It's not the biggest, the baddest, the brightest. It's just one of the stars of the billions of stars. We call it the sun, and around it tonight are orbiting these balls, one of which is called Earth. It's our home. That's you and me. No, I'm not trying to make you feel small. I'm trying to help you see that you are small. But it's significant in significance. Because as tiny as we are known and prized by Majesty, who sent for us and loves us and knows us, even though we are teeny tiny little bitty people on a little bitty speck floating through the vast cosmos that he has made. Just like he could name every star as he called them into being and put them in their places. He could start in this building tonight all the way up in the top with you right there, and he could call you by your name, and he could move to you and call you by your name and you by your name, and the great creator of all the heavens and the earth could move through this auditorium and call every single person in this building by name tonight. He knows us and is aware of us and loves us and has come to invite us into a relationship with him that will never, ever end. You are, but
So I just want to, I think that video is so cool, and it explains, it wraps everything up so well. I think it's in the beauty of studying this creation versus evolution conversation is, yes, it can get scientific at times. It can feel a little heavy and complex at times and intimidating even, but when you really get to studying it, you realize that you were created. You were not a mistake. You were not an accident. You were created by a God who loved you, and not just loved you and took the time to make you like he did a star, but he considered you his favorite creation. He made you in his own image. He didn't make anybody else, any other creature, any star, any rock, no, nothing else that he made other than humans were in his image. But he made you and me, and he knew you by name before you were even born. During those 7 days, he made everything. He knew who you were. And I think that evolution is such a sad thing in so many ways, and that it just says that you were a accident that formed over billions of years from an explosion. But creationism, right there at the start, we find out just how important you are and how great God is that he could form those complexities with his hands. Things that you or I could never do ourselves, but he did it all in a matter of days. And then when humans messed up and we were potentially going to be separated from God for all of eternity, he loved us, our little insignificant creation in the span of the universe. He loved us so much that he sent his own son to die for us. And I think that is absolutely incredible. And so I just want to leave you with those thoughts tonight. Um, if you have any questions, feel free to reach out to me. Let me know. I'm more than happy to answer those questions or include them in later lessons if we're able to. There are no dumb questions at all. This is a complicated topic. Please don't hesitate. Hope to be able to see you all next week at our next lesson.